Application of differentiable dynamic time mapping in human action recognition by Nirataya Kamsemanan and Choluvinati from Siddington International Institute of Technology, Thammasat University, Thailand. What is human action recognition? Okay, human action recognition, or HAR, is a task of identifying specific action performed by humans in videos or images. HAR is crucial component in various applications such as civilian, human-computer interaction, spot analysis, and healthcare. The fundamental concept of the HAR is first action, right? Now, action is a sequence of movement performed by a person. For example, the way that you can tell if a person was playing on a cell phone. You can see that a person pick up a cell phone, look at it, right? The head might be tilted, and maybe the hand gesture, like clicking something on cell phone. So those are the sequence of movement that altogether we identify as an action. Second part is recognition. Recognition is the process of identifying and classifying these actions. The third part of the concept is features, which is descriptive attributes extract from the video frames or images that represent action. The human action recognition that we are talking about is going to be done by using machine learning. So here are the flow chart of how the human action recognition works. Okay, so we have input videos, right? Now the input video, just the video that we capture a person doing certain things, and we want to know what that person is doing. This video then feeding in the process of we call pre-processing, which is going to be the process that we may removing noise, for example, removing the background, resizing, make the size of the video is the same so that it's easy to process further. Normalization, those are examples of pre-processing. Then after that, the model will extract feature extraction. It could be done by handcrafted, teaching the model what to look for, maybe the movement of the hand, or maybe use another model, a deep learning model, to extract the feature automatically. These could be done both ways. Then once you have the feature, we put it together in the action recognition model. This feature extraction that we extract in the previous step, it's feeding into the classifier or deep learning model. This could be done using convolutional neural network, RNN. It could be done using various things so that the features that we extract earlier passing through this model, action recognition model, will tell us what that person is doing. So the output is the recognized action of that input video. What we are proposing today, we are going to use the dynamic time mapping, DTW, to help us create a model that recognize human action, right? So let's familiar ourselves with DTW. Now, DTW is the algorithm for measuring similarity between two temporal sequences, which may vary in speed. DTW is widely used in time series analysis, speed recognition, biometric information. Mathematical formula of DTW is the distance between two sequences, X and Y, right? Now, DTW is the minimum between the distance of little dots. Little, if you go back to the previous page, this little note here, right? Where pi is the warping path, which is a sequence of index pair ij that define mapping between the element of x and y, right? The way that you pair them, right? The x I is the distance. It could be Euclidean distance, could be other things between the element in the sequence xi and yj. Sorry. Okay, the wrapping part pi must satisfy the following condition, boundary condition, where pi 1 is 1, 1, pi k is the last length, big M and big N. It must be monotonic condition, meaning that if I and j in pi, then I pi and j pi in pi, meaning that I has to be less than I pi and j has to be less than or equal to j pi. So meaning that you're moving forward, you don't go backward, right? Step side condition, if I pi and j pi can I pi and j pi can only move to the next one, I plus 1 and j, or I j plus 1 or I plus 1 j plus 1. DTW distance can be computed using dynamic programming. Define cumulative distance, where dij is the small d xi yi plus the minimum of the distance between the previous one, like di minus 1j, di ij minus 1, di minus 1, j minus 1, with the initial condition that d11 is the distance between the first pair. So DTW is then given by dnm, the length of the x and the length of the y. Limitation of DTW. DTW is not differentiable, as you can see, which makes it challenge to integrate it with the gradient-based optimization method, the new method that used that training using the gradient-based optimization. These limitations limit the use of DTW in modern machine learning framework that rely on back propagation. So people come up with new things that called differentiable dynamic time warping, or DDTW. DDTW extended from DTW by making alignment process differentiable. This allows DTW to be used in neural network and optimized using gradient-based method. The algorithm is the core idea. We replace the hard minimal operation in DTW with soft minimal operation. Now, soft minimal operation allow gradient to flow through the wrapping path calculation. Okay, so now the soft DTW, if you remember the one that we have earlier for DTW, this is really similar, but instead of using minimum, we use minimum with gamma pi, right? Pi is the wrapping path like we have before. The distance is just like before. Now, gamma is the smooth parameter that controls the sharpness of the soft minimum approximation. The minimum now here is denoted as the soft minimum operation, defined as the minimum between minimum of a1 to ak is negative gamma log of the sum of the exponent e to the negative ai over gamma. The soft DTW then define very similar to the way that we define DTW, right? But instead of using the minimum, we use the soft minimum. Where the soft minimum is defined as the soft minimum of A, B, C is the negative gamma log of exponent of negative a to the gamma plus e to the negative b to the gamma plus e to the negative c to the gamma. And that is how we define soft DTW. The proposed method. We propose a novel method to identify human action using a deep neural network and dynamic time warping. We focus on developing a model-based human identification method, which means that we transform image so that the body have structure, have model, to intuitively represent body movement. We use pose estimation to identify body joint locations. Thus, an action is represented as the sequence of body joints. Overview of the proposed method training. Sequences of images are passing through the pose estimation technique. Each image is then represented as sequence of body of joints. In one image will be a frame of body joints in 3 coordinates x, y, and z. Then these sequences of joint will passing through the sequence selection, where we will select 2 random sequence of body joints. Each pair will passing through the embedding model to get representation in form of vector. So we will have a pair of sequence of vector represent sequence of body joints. The distance between these two pairs will be calculated using Soft-DTW to get the loss. Now the goal of the training process is to create embedding vectors such that, number one, minimize the Soft-DTW loss for sequences of the same class, and number two, maximize the Soft-DTW loss of the sequences of different classes. Once the training process is done and we get the model that performs the best, now we will use that in the recognition. The overview of the proposed method for recognition is as follows. First, the sequence of image, the unknown image, will be passing through the post-estimation technique as before. So we will get sequence of body joints. This sequence of body joint will passing through the embedding model that we propose to get the sequence of vector representation that represents sequence of body joints. This sequence of vector will pass through the classification model so that it will predict a class or the action of that sequence of image. A classification technique such as k-nearest neighbor can be used to classify a sequence of embedding vector. Now let's focus on the embedding model. It is intuitively to represent each collection of body joints as a graph where each joint is a vector connected to another joint based on the body structure. We therefore propose to create the embedding model based on the graph neural network. Given a collection of body joint F, we represent it as a graph GVE, where V is set of joints and E is set of edges. Each joint is represented by joint location, as shown in this picture. To capture detail of the movement in the different body part, we use multiple graphs to represent body part instead of represent the entire body as one. So we focus on the local movement. For example, we focus on the right arm graph on the pink area here, left arm graph in the blue, right leg graph in dark green, and left leg graph in light green. This graph is then passing through the GNN body, GNN left arm, GNN right arm, GNN left leg, GNN right leg, the graph neural network. Then these results of each area will be concatenated together and passing to the fully connected layer. As a result, we will get the embedding vector V. As a current process right now, we are conducting experiment on multiple datasets, and the preliminary results are very promising. Thank you for your attention.